From the National Institute for Standards and Technology, and today I'm going to tell you a little bit about math as an instrument and really trying to take some lessons from functional programming. Thanks to Ted and the other organizers for the invitation. So these are the three things that I'm going to try and cover in some brief detail. We'll start with instrumental knowledge, and then we'll say a little bit about functional programming, and then we'll close out with a little bit of thoughts about compassion. Okay, so what is math all about? We start out in elementary school, we're learning arithmetic, we go a little higher, algebra and trigonometry. As an undergraduate, or maybe a little before, you get calculus and linear algebra. If you go in and do mathematics as a major, you start learning abstract algebra and analysis, maybe some number theory and geometry. If you keep going into graduate school, maybe algebraic geometry and partial differential equations, who knows what you want to work on. But the really thing I want to emphasize here is that there's a big kind of cut here in the middle. Where below that, we're really focused on instrumental knowledge. So algorithms, calculation, how do we find an answer? And above that, we're primarily interested in definitions and proofs, and more the question of why things are true. So many people in the room are probably familiar with Lockhart's lament. Today I'm going to kind of turn it around and think about a different version. So I don't know if any of you guys are familiar with Ben Orland. He has this blog, Math with Bad Drawings, that I really highly recommend. It's a great place to go look. But here the point is that we talk to mathematicians, and often, there's this joke that, mathematicians often aren't very good at calculation anymore. Maybe we were as kids, but we don't do that anymore. If you like things other than bad drawings as your evidence, here's a paper of Jeremy's. That in the 19th century, there was sort of a de-emphasis, so the emergence of abstraction and a de-emphasis of calculation. There's also this nice quote from Arnold. He says, teaching ideals to students who have never seen a hypocycloid is as ridiculous as teaching addition of fractions to children who have never cut a cake. And the reason I bring this up is because probably many of you know what an ideal is, but many of you don't know what a hypocycloid is. There it is. There's a picture. It's one of these sort of inscribed, the figures that you get inscribed inside a circle by another circle. And then there's also this nice quote from Helmholtz about how inside every great result of mathematics, there's often some core example that really illustrates what's going on. And this was following a talk that he had given where, I've got to leave it out rather than say something wrong. Okay, so now moving on into functional programming. I don't know if you guys know much about it, but kind of the slogan that people usually use is that functions are first-class citizens. So in imperative programming, which is often sort of seen as a contrast to functional programming, we've got lists, we've got strings, and we just kind of step through them and we modify them in place. In functional programming, we do something different. We write functions. And then we apply those functions sort of inside of other functions. And so really the things to keep in mind here, I guess I got to point it this way close. No. So first of all, we've got this red function that is that we're writing separately, and it uses some recursion in here. We call rev within itself. And then the other thing to notice is that we've got this function map that takes in another function as an argument. And so we use that in order to do this functional programming. All right, so now one of the things that functional programming is most famous for is this use of monads. And so monads are constructions from category theory. That's sort of my field of primary interest. And we've got this nice quote: the curse of the monad is once you get it, once you understand how it works, you lose the ability to explain it to anybody else. And so there's the Haskell wiki. So Haskell is the sort of primary programming language of functional programming. And they have this nice timeline of monad tutorials. You can see there's this gigantic growth from a small start. And so this kind of gives us a nice data set to think about the comparison between the way that mathematicians think about monads and the way that programmers think about monads. There we go. Okay, so they occur in both places, so I'm not going to say too much about this, but the idea is that in math you have a category, so a category is some kind of abstraction of functions and function composition, and then you have a map from a category back to itself, and so the kind of canonical example, at least in programming is lists, right? So you can have integers and then lists of integers. You can have strings and then lists of strings. And then there's sort of two ways that you can manipulate these functors. You can either take an ordinary value, that's not going to work, so this eta map takes an ordinary value and then it puts it inside the monad. So think about taking a value and wrapping it as a one-element list. And then you also have this natural transformation mu that lets you take sort of nestings of these operations and collapse them together. So if you have a list of lists, you can combine them together into a single list by just sort of taking out the intermediate parentheses. And so now, what I find particularly interesting here is that mathematicians have sort of always presented things in terms of eta and mu, and there's some good reasons for that. But functional programmers have decided that they don't like that quite as much, and they actually prefer a different presentation. It turns out to be equivalent that uses this bind function. And so I'll say in just a moment what the comparison is here. Just for the sake of honesty, I should point out that this is not really a quote from Philip Wadler. It's a quote by James Irie, who was not mockingly, but who was making a joke. A monad is just a monoid in the category of interfunctors. What's the problem? And this is sort of based on something that Saunders McLean said. Now, coming out of this explosion of monad explainers, Brent Berge was again joking when he said that monads are like burritos. And an actual better description is that monads are kind of like a programmable semicolon. So the idea is that in programming languages like C, the semicolon is the end of a statement. And what monads let you do is end statements in different ways. So sometimes you might want to import some kind of sampling and probability. Sometimes you might want to introduce some kind of parallelism or some sort of interaction with the outside world. And monads give you a way to do this inside functional programming. And so here's the equivalence back and forth. So on the mathematical side, we have a category. On the functional programming side, we restrict ourselves to just a particular category, which is the category of types of our programming language. The objects are the types and the morphisms are the functions, if you know what that means. So we've got this functor that goes from one category to another. That has kind of two manifestations over here on the functional programming side. So one is as a type constructor. So think of M as list. So I put in int and I get in list, get out list of int. I put in string, I get out list of string. And then famously, functors are applied not only to objects but also to arrows, to morphisms. And so that's what this map construction that we did earlier looked at. And so you can see that it takes in something that's an M of X and it spits out something that's an M of Y. So eta and pure are basically the same thing, but now we have this sort of dual presentation where on one hand you can take mu and you can define it in terms of this bind. I actually used the wrong notation there. Sorry for any professional functional programmers. But you can also define bind in terms of mu. And so you can go back and forth between these. And so one question for me is sort of why? Why do we have these two different presentations? And why have we chosen to use them in different ways? This paper by Mogi was really the first one to bring monads into functional programming. But he sort of explains things in terms of the classical mathematical definition. And he does something to explain why mathematicians like that. So it's defined only in terms of functors and natural transformations, which are sort of better for abstract arguments in some sense. And then this was actually not one of the monad explainers, but I thought this was really the best succinct description I could find about why functional programmers wanted to use monads. And it's really this bit about input-output, I/O. So the idea is that in functional programming, your language is lazy. That means you don't want to evaluate something unless you really have to. And it's pure, which means that your functions are sort of real mathematical functions in the sense that you put in an input and you get an output, and if you put in the same input, you get the same output. But that's not the way that functions in an imperative programming language work. So if my function is go and get some input from the user, who knows what the user is going to give back to me? And so here's another sort of toy example. So you print something to the screen, you get an input, file name from your reader, you read to see what's in the file, you turn it into uppercase, and then you print the message. And in kind of naive functional programming, this is what that would look like. Basically, you have to keep track of the state, right? Because you need this pure functionality where the same input gives the same output, you have to thread this state. So we've got sort of, we start with a state 0 and we produce a state 1, and then from that we produce a state 2, and then we put state 2 in there and we get a state 3, and so you get this kind of pyramid of doom. And you can imagine that in any kind of real program that would just be intractable. But we have this do notation with monads that sort of lets us recover the ease and the flexibility of imperative programming. So I'm not going to sort of say too much about why this works, but the idea is that you have this bind operation that lets you take, say, a list and then apply a function that turns each element of that list into a new list. Now you have a list of lists, and you can use the monad to collapse that down into a single thing. And similarly, with sort of states of states of states of states and many other varieties of computation. Okay, so why do mathematicians like join? That's the name from you. Well, we can use it in an arbitrary category, whereas the bind construction, because it uses functions, requires this Cartesian closed structure, which is just an additional assumption. The eta and mu together form something called a monoid. So if you know what that is, you know what it is. It's basically a multiplication structure. And this is something that recurs over and over throughout mathematics. Whereas the structure of bind is kind of idiosyncratic, and it's not something that we recognize from elsewhere. What was alluded to by Mochi there about the abstract calculations is that with natural transformations, we can do these sort of pretty picture proofs by pasting. You've got diagrams that have two-dimensional cells in them, and you can kind of piece them together like a puzzle in order to give your proofs, and those are all very nice. Whereas the presentation in terms of bind, well, it mixes up the Cartesian product and the function spaces and the composition in ways that are sort of not quite as easy to manipulate abstractly. But on the other hand, we've got some problems on the mathematical side that we don't have in the programming side, right? So in the mathematics, we have this explicit nesting, and it actually turns out so I've said a little bit about why functional programmers brought in monads, but if you look at why mathematicians brought in monads, it actually involves this explicit nesting. So there's some sheaf constructions where you want to build a resolution, if you know what that is. So it's basically a sequence of maps. And each one of these maps is sort of a new layer of nesting. Another major application in mathematics is algebraic theories. And so there, we want to be able to sort of apply an operation to the application of an operation to the application of an operation. So polynomials, for instance, right? You can sort of plus and times and get a big tree of operations. And so we like that. But when you're doing programming and you're trying to get things done, it can be very confusing if you're sort of many levels deep in your structure. And we would typically prefer to sort of stay at one layer. It gives us this explicit sequencing that's very useful in the state example that we saw before. It has certain optimizations. So building lists is computationally expensive. And so if you are building lists of lists of lists of lists, you're doing a lot of work that maybe you don't actually need to do. It can also be the case that these things may be much smaller. So if you think about, so there's a power set monad. So rather than lists, we have sets. And if you're talking about sets of Boolean values, for instance, you're never going to have more than 2 of them. But if you have sets of sets of sets of sets, then they can become arbitrarily large. And it's also repetitive. So somehow the mu is a very simple thing that just depends on an identity. And so you have to sort of repeat yourself over and over and over again. Whereas the expression in terms of bind is maybe a little bit more ergonomic for when you're trying to get something done. Okay, and so a good quote that I guess not a quote, but a description that somebody online provided is that you can use mu to understand what a monad is, but you use bind to understand what it does. I think that's a pretty good way of thinking about it. Okay, so now what does that have to tell us about compassion? So again, Breiner, and I really love this guy. So he talks about the house and the tree. So the tree is what's universal about mathematics. You know, there's many of us at least feel that there's some kind of reality there that we go and we discover. And so he says that this is the tree. but we can't access the tree directly, right? We've got these platonic reality that we don't have direct access to. And so we build a house around it of our notation and our conventions, our definitions, and the only way to access the tree is through the house. And so he says he's seen students go sort of around and around and around the circle without ever really sort of finding their way inside. I mean, the tree is inside the house. How do I get inside? Well, just use the door. I don't see the door. Well, the door makes sense if you see the tree. What tree? Right? And so then you just sort of cycle around. So now, why do we do math? Peter Lomstein has this nice quote. Abstract nonsense, that's a sort of another name for category theory, is the garden, then concrete computations are the flowers, right? So we don't care about the abstraction, totally in absence of the things that we're abstracting over. John Baez, who's really one of my sort of personal heroes, has this nice essay, Why Mathematics is Boring, where he takes some conventions from narrative fiction and says, can we apply these ideas to mathematics in order to make it more interesting, more lively? And he points out that, we do have these things, right? But we tend to stick them into our talks or into our conversations, and we often don't put them in the published papers, and that just makes it harder for people to read and understand. But really, right, both of these things are valuable. So Rhoda says, if you're a space engineer and you want to send a rocket into space, then find a problem solver. But if you want someone to teach your child mathematics, or maybe more broadly, then you might want a theorizer, someone who takes that bigger perspective. So now, where should we find compassion in mathematics? Priya is one of the organizers who's sadly not here. She lives in Estonia right now, so it's a long flight for her. But when I first talked to her about this idea of compassion in mathematics, it seemed very clear to me that elementary and secondary education is really the place to go to look for it, just based on numbers and how much time and effort and energy people spend on it. These are just estimates. Don't take them with a large grain of salt. But as I was going through this talk, I realized that this is kind of at least a bit of a blinkered framing, because you don't have to be a student to learn mathematics, right? There's plenty of other people who use mathematics or could use mathematics in their jobs, in their lives, and in things that they want to get done. And that's a pretty big chunk too, right? And so we should think about supporting those people as well. And I think this is my last slide. What is math for? We've got at least two different answers, right? There's this sort of more theoretical answer about using mathematics to find understanding, to understand what's going on. And then there's this instrumental answer about finding answers to the problems that we have in our lives. And I think pure mathematics, sort of modern mathematics, the part of mathematics that lives above that line from the beginning of the talk, has really, for a long time, favored the theoretical side over the applied side. And when we do that, we limit our scope, right? If someone is just interested in getting an answer, then we may need to frame the theory in terms of their question before they're ready to understand it or to want to understand it. And I think we also make it harder to learn, right? Because if we can frame things in terms that people already understand, then they will be more receptive and maybe more able to sort of capture the abstractions that we're trying to show them. And so I think to some degree realizing this broader accessibility mostly needs a cultural shift, right? So it turns out that building these examples, these detailed examples, is a lot of work. But that's not what you get tenure for, right? You get tenure for the theorems that you proved. And so we really need to value the expository and explanatory more, I would say. And I also tend to think, and maybe I won't say any more about this, that we could probably do well with new mechanisms for dissemination. So the projects that are most influential in the world today are very rarely the projects of individuals. if you think of something like lean, like Jeremy was talking about in the last talk, that's really it's a grand effort by many people. And I think we could do well by sort of taking that viewpoint and importing it into our publications. We should think about how we can work together to produce publications, expositions that many people can contribute to and work on together. This is also a great way to bring in younger people, undergraduates, to work on pieces of these things. Just like these big proofs, we could have expositions that have sort of an outline given by an expert, and then details that are filled in sort of as we go. And I think that providing those sorts of platforms would be a good way to provide these kinds of applied and contextual examples for our mathematics. Thank you. I don't know where I am on time, but I'm done.
No, you're done. Yeah, that's good. Thank you.